The slides are visible. It is moving now. Yes. So last class what we understood is that the rotor is running lesser than the synchronous speed, and during start where speed of the rotor is 0, so slip is equal to 1, and slip cannot be 0 because the motor stops. So the range of the slip is 0 to 1. That is the range of the slip ideally, but normally no. The motor is designed for the slip of 1% to 5% or 2% to 5%. It all depends upon the manufacturer how they are designing the motor, right? So now, so the difference between the rotor speed and the stator speed, that is nothing but is defined as slip. So that slip now, it is having some effects on the rotor parameter. So the difference between the rotor speed and the stator speed, how it is affecting on the rotor parameter. So rotor parameter means what I am calling is that these are all the rotor parameters. So what will happen to the rotor frequency? Because it is the AC machine, rotor also is having induced EMF. So rotor also having current. So what is the frequency of that induced EMF and what is the frequency of the rotor current? So because of the rotor is not running with synchronous speed, it is running lesser than the synchronous speed. Because of that you have slip. So what are all the effects of slip on the rotor parameter? So what it is doing on the rotor? So what it is doing on rotor frequency? So that we have to understand, and what it is doing on the rotor induced EMF, and of course rotor current and rotor resistance, rotor reactance and rotor power factor. So what this difference is doing on the slip? Sorry, what this difference is doing on the rotor, that we have to understand. So one by one we will take this parameter and we will analyze. First we will take the rotor frequency, right? And if you take rotor frequency, or if you take rotor EMF, resistance, reactance, when the effect of slip is coming on the rotor? Only during the running condition, right? Starting condition, slip is equal to 1, but only during the running condition it is having some, or in other words I can say like this, it is having influence on the rotor parameter both during the starting condition and also during the running condition. The effect of slip on the rotor during starting and running condition, it will not be same. I can put like this. Why the effect of slip on the rotor parameter will not be same during the starting and running condition? Because the value of slip is equal to 1 during the starting condition and the value of slip ideally 0 during the running condition. But hypothetically it is not possible, but ideally no, it is 0. So since the slip is having two range of values, so I can say that the effect of slip on the rotor parameter, it is divided into two. One during the starting condition, another during the running condition. So we have to analyze the effect of slip on the rotor parameter during the starting condition and also during the running condition. So one by one we will take. First we will take the rotor frequency. Okay. So if you take the rotor frequency, so I have to define certain parameters now. So let me assume let F is the stator frequency. So that is the supply voltage you are giving as the input to the stator. So F is the stator frequency. We have to assume certain notation. And since the effect of slip on the rotor is varying during the starting condition and running condition, let me define F2, that is the rotor frequency under starting condition. Let me assume F2 is the rotor frequency under starting condition. Under starting condition, or in other words, I can say under standstill condition. And let me assume F2R, that is the rotor frequency under running condition. Under running condition. So now, what is my synchronous speed? Synchronous speed is nothing but it is 120 F by C. Let me take this is equation 1. Right? The same expression, if I want to write for the rotor frequency under running condition, how I can write? So 120 F2R will come here. So the same expression 1 I am writing for rotor frequency under running condition. So F becomes F2R, P remains same. What I should write in the place of NS? Anybody? NR? Only one answer I got. This is right. Because everybody will have in our mind, it is the rotor frequency under running condition. The rotor is rotating. So definitely that is equal to NR. Right? Everybody will have that in our mind. Now I will ask this question whether it is NR or NS minus NR. The rotor is rotating. It is rotating because of what? The frequency with which the EMF induced in the rotor, that is the rate of change, that is because of rate of change. Because of that only the EMF is induced in the rotor. Yes. So it is because of the relative speed between the stator and the rotor. Because of that only the rate of change, that is the frequency with which the EMF is induced. So it is not simply NR, it is NS minus NR, right? See, all these things, how they have arrived is that simply, you have to measure all the parameters experimentally, right? You have to measure rotor frequency, and you have to measure stator frequency, and you have to measure the this NS, NR. Experimentally, if you measure all these parameters, and if you see this rotor frequency, that is proportional to the difference between the synchronous speed and the rotor speed. It is coming like that experimentally. So once it comes experimentally, then only people realize, oh yes, it is right. So the rotor frequency is coming as the difference between the stator speed and the rotor speed. It is coming like that. Yes. So why it is coming like that? Then only people understood that yes, it is right. The rotor is rotating. The frequency is the time domain. That is the rate, the change. That is because of the relative motion between the stator and the rotor. See, everything, no, they have not understood from heaven or hell, right? Everything through experiments, they coined all this expression. So this F2R, it is not simply proportional to NR, it is proportional to NS minus NR. Any doubt in this? Are you understanding this point? Yes. See, even when I read this first time, I got this doubt. Everybody will have this doubt, right? Because this machine, strictly speaking, no, I am taking, this is 10th time I am taking this mission, right? 2012, I joined my job. So from the 2012 onwards, I am teaching mission. Maybe 10th time or 8th time or 9th time, I do not know. So many times I have taken this electrical machines 1 and electrical machines 2 for different students. Even when I read this concept first time, I had this doubt. It should be equal to NR only. Why they are writing NS minus NR? Okay, then only I realized that yes, oh, it is the relative motion. Because of that only the frequency we are getting it on the rotor. So it cannot be as such is equal to NR. It should be the difference between NS minus NR. So let me take this equation as 2. You divide 2 by 1. What is that I will get? Simply note this, you can write simply like this. F is proportional to NS. Simply you can write, because 120p, both are constant, and F2R, simply you can write it as NS minus NR. Proportional, it is proportional. If you divide 2 by 1, what I will get? What is my F2R? What is the rotor frequency under running condition? What expression I am getting? Tell me, man. Yes, S into F. So what we understand from this expression? Yes, yes. When the machine is about to start, slip is equal to 1. Am I right? So when the machine is about to start, what is the condition? Am I correct? So I can say when the slip is equal to 1, that is the motor is about to start. So that condition I can say it as it is the starting or standstill condition. Right? So when the machine is about to start, your F2R becomes F2 because F2 only we have taken as rotor frequency under starting condition or standstill condition. That is becoming equal to F itself. So when the machine is about to start, the frequency of the rotor is same as the frequency of the stator. Are you understanding this point? So whatever the voltage with the frequency you are giving as the input to the stator, so during the starting time, the induced EMF or the current is having the same frequency as to that of stator. Right? This is very, 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 very important. So during starting condition, the frequency of the rotor is same as the stator frequency. So during the running condition, the frequency of the rotor is getting affected by slip. Right? So this is very, 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 very important. So now you take this example. You take the stator frequency is 50 Hz, right? And under running condition, you assume the slip is 2%. So what is the rotor running frequency? What is the value I have written here? 1 Hz, right? That is the rotor frequency under running condition. That is very, 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 very small. Am I correct? It is only 1 Hz. The slip is doing such kind of effect on the rotor during running condition. What is the value of frequency under standstill condition or starting condition? Simply it is equal to stator frequency, that is 50 Hz, right? So under standstill condition, your rotor frequency is 50 Hz, and under running condition, the rotor frequency is equal to 1 Hz. So how, or in other words, how much effect the slip is doing on the rotor in induction motor, you can very well understand from this example. See, almost the rotor frequency is looking like DC when compared to the stator frequency. Am I right? During running condition? Yes or no? 1 Hz is very, very small. Almost the induced EMF or the current during running condition, it is almost looking like DC. Am I right? Yes. So that effect is doing on the motor during running condition. That is what we need to understand, right? So this is the effect of slip on the rotor frequency. Now we have to understand what will be the effect of slip on the rotor induced EMF. Any guess? Heuristically, can you write? Any guess? But man, nobody is saying. Rotor induced EMF. That is the next parameter. That is the next parameter. Rotor induced EMF. Similar to rotor frequency, heuristically, can you write the expression for rotor induced EMF under running condition? You assume E2, that is the rotor induced EMF under standstill condition. Same analysis only. Rotor induced EMF under standstill condition. Similarly, you take E2R, that is the rotor is induced EMF under running condition. Heuristically, can you write the expression similar to the rotor frequency? Anybody can tell me? What would be E2R? Yes, very good. S into E2. Right? See, it is also true for induced EMF. E2 is proportional to the frequency. Again, no, the induced EMF depends on the frequency. Again, the E2R is proportional to that difference, NS minus NR. That is proportional to F2R. Because frequency is the main parameter on which only the induced EMF is dependent. So directly you can write E2R is equal to S times E2, right? Then what is the next parameter? Rotor resistance. So what about rotor resistance? Same thing you assume. This is R2. That is the, I don't want to write again and again. R2 is the rotor resistance under standstill condition. R2R, that is the rotor resistance under running condition. What is R2R? S times R2. Why? Why it has no effect on the resistance? It is right, but you put it in a right way. The resistance is independent of the frequency parameter. Am I right? Yes. Induced EMF, no, it depends on the frequency. But the resistance, it is not dependent on the frequency. It is independent of the frequency. Right? So, R to R, it is not having any effect on the slip because slip, no, that is the frequency parameter. So, since the rotor resistance, it is independent of frequency, it is independent of frequency. Because of this, the rotor resistance will not change. It remains same during the starting and running condition. Okay. And the next parameter, rotor reactance. What about the rotor reactance? Very good, very good. Why? Because the rotor reactance, no, it is dependent on the frequency. Because the rotor reactance is nothing but X is nothing but 2 pi FL. So the reactance, no, it is dependent on the frequency. So I will assume X2, that is the reactance under standstill condition. X2R, that is the reactance under running condition. Since this reactance, no, this reactance, it is 2 pi FL. Because of this frequency below only, the rotor reactance during running condition will be different from rotor reactance during the standstill condition. So X2R becomes S times X2, right? The next parameter, rotor power factor. This is reactance. Rotor power factor. Power factor, how we can define? What is power factor? How we will define power factor? Yes. So here um, you assume like this. Power factor is cos pi 2. That is the rotor power factor under standstill condition, and this is the rotor power factor under running condition. So if you write the rotor power factor under running condition, this is resistance under running condition, that is directly equal to R2, because resistance, it has got no change during the standstill and running condition, divided by your Z2R. What is your Z2R? So this one simply I will write R2R, because here notation we are using R2R, no? So I will maintain the same tempo here also, right? So R2R is equal to root of R2R the whole square plus X2R the whole square. So this one I can write now. R2R is nothing but simply R2 divided by root of, this is simply R2, but this X2R I can write S times X2 the whole square. So this is the power factor under running condition. So what is the power factor under starting condition? So simply you put slip is equal to 1. So R2, this is for starting condition or standstill condition. So divided by R2 square plus X2 square. So this is the power factor. What about the rotor current? Rotor current, how we will define? Rotor EMF by impedance. Am I right? Yes or no? So rotor current similarly I can write. So R2R, this is equal to E2R. That is the rotor induced EMF under running condition divided by impedance, Z2R. So this one I can write S into E2 divided by root of R2 square plus S X2B whole square. What is I2? I2 is the rotor current under standstill condition. So whenever you want to get the condition under standstill, simply you substitute slip is equal to 1. So E2 divided by R2 square plus X2. So what ultimately we need to understand is that during the running condition, the rotor parameter is getting affected by slip because of the frequency only. And rotor resistance alone, it remains same because it is independent of frequency. So this we need to understand, right? So all these things I have discussed. Yes. So we studied construction of induction motor, and then we studied the rotating magnetic proof, and this one synchronous speed, and the effect of slip on the rotor parameter. Now, as usual, we have to derive the torque equation of the induction motor, right? I already told you that if the output of any machine is mechanical in nature, generally we will derive the torque equation, right? If the output of any machine, if it is electrical in nature, generally we will derive the EMF equation. So here in the case of motor, we have to derive the torque equation, right? So torque equation, no, we can start like this. So what is the torque equation of DC motor? Torque is proportional to phi into Ia, right? Very crude way we can understand this. Torque is the interaction between the flux and the current carrying conductor which is placed in that magnetic flux. So because of the interaction of these two only, you are getting the torque. So simply I can write torque is proportional to phi into Ia, right? That is in the case of DC motor. But induction motor is AC motor, so power factor will come into picture. So in the case of induction motor, we can write torque is proportional to phi into, and in the case of DC motor, that is armature current, but in the case of induction motor, it is rotor current under running condition, right? And of course, it is an AC machine, so power factor also will have effect on the torque. So you want to multiply this phi I into power factor, that is cos phi 2 R, right? So now the torque equation of induction motor, simply I can write like this. So torque is proportional to phi into I2R into cos phi 2R. So this is the rotor power factor. This is the rotor power factor, right? So here the flux which is produced by the stator, no, that is proportional to stator induced EMF, because how much voltage you are giving as the input to the stator, that much amount of induced EMF only you will get in the stator. So because of that induced EMF only, you will be getting the flux. So the flux is proportional to E1, that is the stator induced EMF. And E1 and E2, no, both are proportional to each other, right? So how much amount of E1 you have in the stator, that much amount of E2 only you will get in rotor. All are proportional. So simply this phi, no, instead I can write proportional to E1 or I can write proportional to E2, rotor induced EMF. So you substitute in the place of phi E2. So torque is proportional to E2 into I2R into cos phi 2R, right? So now torque is proportional to E2, okay? And what is my I2R? I2R is nothing but S into E2 by, you just substitute the expression for I2R, okay? You just substitute the expression for I2R. S into E2 divided by root of R2 squared plus S into X to the whole square. And what is the expression for cos phi 2R? Cos phi 2R is nothing but R2 by root of R2 squared plus S into X2 squared. So just to simplify everything. So if you simplify, you will get torque is proportional to S E2 squared into R2 divided by R2 squared plus S into X to the whole square. So that is the expression for the torque, right? And we have to introduce one constant of proportionality, no? So torque is proportional to S E2 squared R2 by R2 squared plus S into X2 squared. Or I can write torque is equal to, simply I can write torque is equal to K S E2 squared R2 by R2 squared plus S into X2 squared. So we have introduced one constant of proportionality K here, and you can derive the value for K. That one I'm not going to do. You can refer B.L. Tereja book, how to derive or how to get the value for K. Directly you can take the value for K. K, no, if you derive, you will get 3 by 2 pi ns by 60. So that is the value of K, right? So torque is equal to K S E2 square R2 divided by R2 square plus S into X2 square, and K is the constant of proportionality, and you can derive the value for K. So K is coming around 3 by 2 pi ns by 60, and ns is the synchronous speed. So now this is the torque equation. Now this E2 I can write like this. So here I will rub everything because it is simple. So this equation is there, no? This torque is equal to K S E2 square, or torque is proportional to S E2 square, whichever equation you can take. Now this E2 I can write in terms of E1 like this. E2 is nothing but AT into E1. AT that is the turns ratio. That is the turns ratio. Or in other words, E2 by E1. E2 is the rotor induced EMF. E1 is the stator induced EMF. That is differing by the turns ratio of stator and rotor. The turns ratio I am representing as AT. Generally, we will represent turns ratio with the help of notation K. But K here we have already used as the constant of proportionality, right? So we have to use some other notation. So we are using the notation for turns ratio as AT. So E2 by E1 is equal to AT. What you can understand from this? Can I say induction motor is a transformer? Yes or no? Huh? Yes. Because the induction motor working principle is very similar to transformer. Am I right? See, transformer, you have primary side, you have secondary side. Everything is stationary there, right? How the EMF is getting induced in the secondary side? Due to the mutual induction. Due to the mutual induction, right? Here also, the primary side of the transformer is very much equivalent to the stator of induction motor. Am I right? There also you have winding, here also you have winding. Am I right or not? And the secondary side of the transformer is static there, but here the secondary side of the induction motor is rotating. That is the only difference. Am I right? Yes or no? So the induction motor, since it is working based on the transformer working principle, I can call induction motor as rotating transformer. Please note down this. Induction motor, since it is working based on the transformer principle, induction motor, in other words, it is called as the rotating transformer, because some difference we have to give. There everything is static, but here one side is static, other side is rotating. So the induction motor, in other words, it is called as rotating transformer. So in that sense, I can write the induced EMF E2 with respect to E1 in terms of turns ratio. So E2 by E1 is equal to AT. So simply this E2 I can represent like this: AT into E1 the whole square, right? And this E1, this is also equal to V2 by V1. Can I write like this? E2 by E1 is equal to AT is equal to V2 by V1. Transformer we have written like this. Do you remember? Yes. So this E2 by E1 is equal to AT, that is equal to V2 by V1. So this E1 I can write in terms of V1, right? So the torque equation now it becomes S into AT V1 the whole square R2 divided by R2 squared plus S into X2 squared, right? Now the torque equation we have written in terms of stator input voltage. What is V1? V1 is the stator input voltage, right? So finally the torque equation it is becoming like this. So torque is equal to K times S into V1 squared R2 divided by R2 squared plus S X to the whole square, right? So here I think I missed one 80 here. Sorry, yeah, 80 will come here. Okay. So T is equal to K S A T V1 squared R2 divided by R2 squared plus S into X to the whole square. And what is the value of constant of proportionality? T divided by 2 pi ns by 60. And whatever the torque equation we have derived here, the torque equation we can call that as running torque equation, right? That is the torque during running condition. So instead of writing T, you can write T2R like this, right? So the torque during running condition is nothing but KSAT V1 squared R2 divided by R2 squared plus S into X to the whole square. And sometimes, mostly in the case of induction motor, the turns ratio will be equal to 1 only, right? Generally, no, your AT that will be equal to 1 only, okay? Because in the case of transformer only, we need stepping down or stepping up action. Am I right? Induction motor, no, we are not much interested to step up or step down the voltage. We need only the rotation, only the motion, right? So unless otherwise very special purpose requirement is there, we'll always maintain the turns ratio as 1 only. So simply no, everybody know they will write the torque equation as K times S V1 squared R2 divided by R2 squared plus S into X2 squared. They maintain the turns ratio is equal to 1, right? So this is the torque equation under running condition. So how to get torque equation under standstill condition? Now the torque also is depending on the slip, right? The slip is having two values, one during starting, one during running condition. Now how to get the expression for the torque under standstill condition? Simply you substitute S equal to 1 in the running torque equation. So if you substitute S equal to 1 in running torque equation, then that expression becomes torque equation for standstill condition, right? So remaining thing we will see it in the next class.